Greetings, everyone, and thank you so much for joining today's webinar. Today we're going to be discussing coordinating RF in the corporate environment. But before we get into that, just a few items of housekeeping. First of all, this webinar is being recorded and will be available for on-demand viewing. It usually takes us about a week or so to get it edited and ready, but when it gets ready, you can find it at shure.com/webinar. Once again, that is shure.com/webinar. That is a great place to go. You can see all of our past webinar archives. We have a lot of webinars across a lot of different audio topics. It's also where you can see all of our upcoming webinars. So feel free to visit there, see what we've got coming up, and see what we've done in the past. Second of all, as we go through the session today, if you have any questions, please type those into the Q&A section of the webinar panel. We will hold on questions until the end of the session, so type in those questions, be patient, and we will answer as many as we can at the end of the presentation. So speaking of the presentation, let's dive right in here today. Today, our fantastic panelists are Vanessa Jensen and Michael Moore. And on this screen right here, you'll see those QR codes. If you want to pull out your phone and scan those will take you to their LinkedIn profiles so you can connect with them and, ask them questions separately after this session. And let's take a look really quick at our agenda. So we're going to start by talking about the RF spectrum. Then we're going to talk about current bands in use, planning considerations, successful deployments, and then, as I said, Q&A at the end. So that wraps up all of the boring stuff. Let's get into the learning. Take it away, Vanessa.
All right. Thanks so much, Cheryl, for that awesome introduction. So today we're going to jump right into an overview of the RF spectrum. So we're going to move on and talk a little bit about spectrum regulation. So what we're talking about here in terms of wireless microphone operation, we're talking about radio waves, right? And those are found on the electromagnetic spectrum. Now that spectrum is going to have radio waves on one end, we're going to have gamma waves on the other end, and we're going to have some visible light somewhere in between. We're not going to get into all that physics and sciencey stuff. We're just going to give you a quick overview of the spectrum that we're using for wireless microphones. Keep in mind that the demand for wireless solutions, right, is extremely high. We've got governments that are regulating the use of this spectrum, right? So this is going to vary a lot based on your location. The bottom line here is that the spectrum that we're utilizing as a wireless microphone operator is limited, right? It's not going to be an infinite resource. It is very, very finite, and we are going to talk through what spectrums are available to us as wireless microphone operators. In terms of the spectrum itself, here is a quick peek at the US wireless frequency bands for wireless microphones. What you'll see here is on the lower end of the spectrum, all the way on the left-hand side of this chart, you'll see VHF, right? The very high frequency range. So that's coming in around 174 to 216 megahertz, or so. And then as we sort of move up, we have the UHF range. We've got some cellular bands in there. And then we've got a few other bands called ISM, STL, DECT, and all the way on the upper end, we've got things like 2.4 and 5 gigahertz, which you should be more than familiar with from your wireless at home. We're going to dive into the specifics of each of these bands, the pluses and minuses, if you will, so that we can kind of determine the best place for our microphones to play. Of course, I mentioned earlier on the first slide there that we're not the only player in this frequency spectrum, right? There are a ton of other users. There's a lot of competition in these bands. So basically, we have things like digital television. So we've got major broadcasters there, right? We've got lower power local television stations, right? Your PBS, your more local type applications there. We also have things like public safety communications. These are all going to be things that are used for fire, police, EMT. So we've got those very important communications also happening in this spectrum. We've got other manufacturers, right? Shure makes microphones. A lot of other manufacturers make wireless microphones, other devices as well falling within this spectrum. Utilities, things like 4G, LTE. Bottom line here, we are among many other users within this spectrum. And there are global considerations to keep in mind. For the sake of this webinar, we're really going to focus on US frequency bands. So really, depending on your location, rules, regulations are going to vary, right? Some countries are very lax. Others can be extremely regulated. So as a global organization, we've got offices. We've got representatives in 30 countries worldwide. We've got a team in place to answer any questions you might have. So if you're joining us from elsewhere today, please reach out to us at any time. We're happy to provide you with some guidance. So with that in mind, and all of that spectrum at the very top of the chart there for us to choose from, how do we know which one is the best for our application? So we're going to jump into some of the specifics of these bands. So we're going to start with VHF. So as I mentioned earlier, VHF stands for very high frequency, and that's going to refer to electromagnetic waves in that 49 to 216 megahertz range or so. So it's very important to keep in mind as we talk through sort of the advantages and disadvantages that this particular spectrum, right, these electromagnetic waves tend to be more susceptible to noise. So there's going to be a higher noise floor with VHF type equipment. Definitely want to scan for any noise that might impact your system performance. Almost any piece of electric equipment is going to cause that noise, and it's going to add up. That noise is going to degrade your signal to noise ratio. We always want more signal than noise. So it's super important to keep in mind that this may come with a higher noise floor and that you want to scan to see what is going to be available in your area. Additionally, because of the properties of this particular wavelength down on the lower end of the frequency spectrum, we have a longer wavelength. And those longer wavelengths are going to require larger antennas to capture that energy. Now, what does that mean for you? That means that if you're looking for a portable, mobile type solution, this may not be the best for you unless you like carrying larger antennas. So keep in mind that if this is a fixed install, it's going to work just fine. But again, those larger antennas may limit your portability. And I think overall, even though it's a narrow slice of spectrum, the benefit here, the key benefit is that if you are in a really crowded RF environment, this is going to bring some additional flexibility to get you some more wireless microphone channels in aspects or landscapes that may not have as much noise. So again, scan, scan, scan. We're going to move on to ISM. So ISM itself is actually a license-free range that is reserved for industrial, scientific, and medical devices. There are bands that are regional as well as worldwide. In this case, in the US, we're talking about 902 to 928 megahertz. You'll see that on the upper right-hand corner, highlighted in green there. So this is going to accommodate smaller channel counts. It is license-free. So keep in mind that there could be other devices that are operating in this band that might cause interference. Again, smaller channel counts, great in that it is license-free. Proper planning, always important. Lastly, on this slide here, we'll bring it on home with STL. The STL band stands for the Studio to Transmitter Link, predominantly used in the US by broadcasters for transmissions between basically a studio and that station's transmitting antenna. It's a very narrow slice of spectrum, right? So you're seeing there that we've got that 940 to 960 megahertz range, and it does require the use of a license. So that could be a benefit. It could also be a disadvantage as well. But if you're using this in a fixed venue, it is a great way to realize additional channels of wireless microphones. And with that, I'm actually going to toss the baton over to Mr. Michael Moore to tell us about UHF.
Thank you, Vanessa. Thank you, everybody, for your time today. Next part of the spectrum is UHF. And so a lot of the previous concerns in regards to safety and DTV, this is where a lot of it is found. Now, this is obviously the biggest slice of spectrum on this chart that's usable, which also means, as Vanessa said, a lot of other manufacturers play in this range. And there's good reasons because of propagation, the quality of audio, the amount of data now that we're digital, and the distances that are very flexible is why UHF is really kind of the sweet spot of RF audio. It is a very wide tuning band, as you can see. This also allows us, because we're using discrete frequencies that will be tuned, that we'll talk about a little later of how that tuning happens. This allows us to create multiple zones by utilizing antenna distribution. So again, like some of the other products that we're going to talk about in some of the other ranges, some of this is not necessarily possible just because the way that that you have to utilize that specific part of the spectrum. Of course, within this range too, with just a nod to rechargeable accessories as well. It's a great piece to save money, save the environment. And of course, you do have some flexibility because most of this is technically a one-way transmission. There are ways to add other devices for certain models to have back channel communication down to the transmitter itself. And again, unlike other parts of the spectrum, frequency coordination is a must, but don't worry, we will talk about that here in a few and show you how simple and quick and easy it is to do coordination in the UHF spectrum. Now, moving on, I'll kick it back over to Vanessa to talk about our next part of the spectrum.
Thank you so much. That was a great overview of UHF. We're going to jump into DECT, which stands for the Digital Enhanced Cordless Telecommunications. Say that fast 3 times. This was originally developed for cordless telephone systems. Anybody remember those? So the ranges that is going to be used by the DECT band is really going to vary by country. So here in the US, it is 1920 to 1930 megahertz. Let's talk a little bit about some of the disadvantages of this. So it is an unlicensed spectrum. What does that mean for you? If you're in a corporate environment, there are tons of other devices that could be utilizing this spectrum as well. Things like office or call center headsets are also going to operate in this spectrum. So it's really important to know whether or not there's a call center next door or down the hall, because that would be something that would be good to know before we put in an MXW or DECT type system. So again, scanning super important. We talked a little bit about wavelength earlier, but here it is higher frequency, shorter wavelength, going to go a little bit shorter distance than something like our UHF range. So that is important to know as well. If you're using this in a corporate type environment, typically that is not going to be an issue, right? Your meeting rooms, your conference rooms, those types of places are going to be more than sufficient in terms of utilizing this type of a frequency range. And also as part of that DECT protocol, we also have a little bit of latency. Again, if you're using, using this for video conferencing, it's not going to be problematic for you in most cases. It is certainly going to work for those types of applications. So it's unlicensed. Again, be aware of that because there are potential for other interferences. What is a key benefit here is that it is going to provide some automatic frequency coordination. So we don't actually have to worry what channel we're operating on specifically here. If there is spectrum, the system will act to avoid any type of interference, which is a great benefit if you don't want to get into, manually planning your frequencies with a larger install. It is very efficient in terms of utilizing that spectrum. So we've got the 10 megahertz there. And with that, that allows us to accommodate 40 to 80 channels max in that piece of spectrum. So it is a pretty high channel count within that DECT range. And this is going to be available in almost every country. Again, it's maybe a different frequency range depending where you're located. So let's kick it over to Michael Moore to talk about the 2.4 and 5 gigahertz range. Michael?
Why, thank you, Vanessa. Now, this is a webinar specific for corporate environment. So we do want to add a little bit of a disclaimer here that 2.4 and 5 gig normal wireless devices, we typically do not recommend for corporate environment just because that part of the spectrum is already utilized very heavily with other devices within the office space. However, when we talk through this, we are talking a lot about the benefits that we have in 2.4 and 5 gig in the corporate environment with our MXCW product line. Now, just like DECT, it is an automatic frequency management. It is not a licensed Wi-Fi device. So this adds a level of security that cell phones, that other wireless devices cannot access these systems. So again, even though it's in that spectrum that we utilize for our wireless connectivity, your only way to access that specific product is going to be through a hardwire. Specific again to MXCW, not to get too product centric, is DFS, which is dynamic frequency selection. Now, this is specific to the 5 gig part of the spectrum. And what this allows us to do is leverage a part of the spectrum that your traditional Wi-Fi devices do not have access to because they're just simply not tuned to operate in that area. So we're allowed to leverage these small parts of the spectrum with certain technologies like this to be able to take advantage of it, of unused spectrum. Now, obviously, it is highly utilized. It is a shorter wavelength propagation. So again, unlike UHF and more similar to DECT, based on where you can install access points and the size of room or open space, these are all things just to take into consideration when utilizing this part of the spectrum. And of course, the nice thing is it is an unlicensed use. So again, for folks that are in parts of the world where you do have to pay to reserve frequencies or utilize frequencies, there is unlicensed use of this part of the spectrum. Now, moving on, just to kind of wrap all of these up into one, this is just a quick overview that can be found on our website. And again, you'll see here on the chart, and the big takeaway is our spectrum is not necessarily growing right now. This is where we're at. We obviously, for folks that are familiar with the 700 meg, the 600 meg sell-off that's happened over the last 15, 20 years, even though we have lost a lot of traditional UHF landscape, by switching to digital product, which you see here, essentially everything is a digital product, gives us a much more efficient transmission that allows us to stack a lot more devices closer together. So yes, we've lost spectrum, but the good news is we can start to stack a lot more channels more tightly together. So again, just a quick reference to show that we're trying to leverage all parts of the spectrum that we can use. Of course, taking in to the comments about certain parts outside of UHF, just understanding more of when to use it and how to use it are important. Now, the next thing that we want to talk about moving into successful RF planning is really just a few general ideas that when we start to talk about wireless microphone planning, kind of 4 central ideas just to think about. So the first idea is going to be your channel count. So again, as Vanessa spoke about certain parts of the spectrum where there's smaller slices of spectrum that you may have to leverage because your area has a really high noise floor. You're trying to get a lot of channels in one building versus on one floor versus across a huge campus. You really need to kind of understand what that usage is and how many of those are going to be used simultaneously. And then, of course, proximity is going to play into that as well, because, again, that environment, which is a limited RF spectrum, we need to know how close we are based on the transmission power that you're using from those devices. And of course, just to remember too, that if you're adding channels to an existing system, it's important to bring this up with your system designer, existing channels of wireless, so you're not caught off guard if you find that you're all of a sudden out of space. Now, the next part of this pie is going to be the usage. And this is just to kind of briefly talk about the features of the wireless devices. Not all wireless devices have the same feature set on them, but just to kind of understand if it's a true self-service room that you're setting up versus a managed space where somebody will be in there to help prepare the room or run the meeting. And then, of course, remote managed. As we see more and more devices go onto the network, we want to be able to potentially remotely mute or unmute microphones from, say, a help desk or a knock or anything like that. So again, just kind of understanding some of your use cases will kind of help guide your decision on that. Now, moving to our next slice of the pie is going to be application. So again, these kind of overlap a little bit with usage and application, but again, flex spaces, training rooms, meeting rooms, mission critical. These will sometimes define what level of wireless do I need to provide for my customer, for the end user in the room. If it's for example, mission critical, that's going to be a global broadcast, there's specific wireless that we would recommend for those situations, just because you know that this is something that will be streamed out to a lot of folks. It's a very high pressure situation that's going to be archived. So we want to make sure that you've got the best wireless out there possible. And then of course, the final part of the pie is going to be transmitter type. So again, just understanding what your options are and understanding which lines offer you handheld, a headset or a lapel body pack type mic, and then of course the traditional boundary and gooseneck as well. So those are just some things to think about when you're in your planning stages. Now, another part of this that we want to talk about, we'll try not to go too deep into the weeds engineering wise, but RF infrastructure has sometimes been a little bit misunderstood. Sometimes there's been things where in the past, because we had a lot of wide open space, we just kind of could stack stuff up and put antennas everywhere and things just kind of worked, or they didn't work. So when you look at RF infrastructure, a lot of the antenna distribution, which is what we're going to focus on today, is not necessarily an accessory to the system. This is a very important part of a multi-channel system when you're talking about UHF product, VHF product as well. Now, one set of antennas can cover multiple receivers. Remember that all of these devices are tuned to specific frequencies when we talk about UHF. So that antenna bandwidth that receives that signal can receive all of those signals simultaneously because they're all tuned to a separate frequency. So sometimes there's this idea that I can only use a certain number of antennas with a certain size system. And so that's one of the reasons it's important to understand antenna distribution. Part of it too is when you get multiple antennas really close together, it actually starts to distort the way the antenna receives the signal. So again, we want to be really efficient in our reception and also be able to put the antennas in the proper location to receive the maximum amount of signal from the transmitting device. And of course, the other part of this too is with distribution, you can expand larger systems to multiple zones. So we're just going to walk through just some basics of the math of how this gets figured when you're calculating for this. So if we've got some engineers on the line or folks that are super interested in calculating antenna system gain, this is how you do it. And by the way, want to just let you know as well that if you're looking at systems, Shure support great folks that understand all of this. So as you're putting your designs together, I know there's a lot of numbers on here. They can help you with this. And so the way that this is basically figured is going to be antenna gain. And what we mean by antenna gain, which you'll see the -3 to +12 there on that paddle antenna, that is an active antenna that actually has an amplifier built in at the antenna itself. So what that amplifier is making up for is what you see as you follow that line down to that -7 dB is the cable loss or the run. So if you've got a really long run, again, we won't get into it today, but making sure that you've got the right cable type as well, because of the loss that you will experience with certain types of cables based on length. That amplifier is there to help make up for some of that loss. And then of course you'll see the +6 to +12 there. That is an inline amplifier. So all that's doing is just simply trying to boost that signal and then finally going into the back of that receiver. Now, obviously this is just simply showing one antenna line. You would have two of these mirrored potentially if the runs are about the same. So your basic equation of antenna gain plus any amplifier gain minus the cable loss, and then of course split loss where we've inserted the amplifier, you might get a little bit of loss there, or if you're having to do a split somewhere else, you really want to have at the end of the day ±3 dB of gain. So plenty of math. We've got a whole one-day course on this if you would love to learn more, but this is how basic and quick and simple it is. And again, as you're designing systems, feel free to reach out to us if you've got a system where you're trying to do something like this with a very long run. We'll be happy to look over it for you. Now, moving on to our antenna distribution, you'll see here this is a level 1 distribution. So again, that box at the top that has the green and the white lines to it from one set of antennas, which, by the way, those antennas that come in the box with these are ULXD model receivers that are shown here. Those can be used. You don't always have to purchase additional antennas based on where your environment is. So again, you can have something as simple as this half-wave antenna connected directly into the distribution box, and then what this is doing is just simply making sure that that signal being received from the A diversity and B diversity are just equally amplified and then sent down to each receiver. So in this simple example, you've got 4-channel receivers times 4 receivers. That's 16 channels of wireless running off of a single set of antennas. Now, one thing that always comes up in corporate AV is multi-room antenna distribution. And so we just want to show you real quick kind of how quick and simple how we can do this distribution. And so you'll see here that it's really as simple as just having an A and B. Again, you need to have 2 diversity in each location, feeding back into the distribution box and then feeding down into your wireless units. And so what's nice about this, and again, this is specific to UHF, but the nice thing about this is that if you're never going to use say more than a few channels in each room, or you might have, say you've got goosenecks associated with these receivers, and you need 16 in room A, and and then the next day you need 16 in room B. This is a way to leverage your investment on wireless to be able to utilize these 16 channels in either room or simultaneously, or combine the 2 rooms, and you can utilize all of the wireless together. So again, really efficient distribution planning will help you maximize your investment of your wireless. Now, finally, we're going to go to a larger scale system. You will get into situations where once you get past a few antennas, really kind of that simple combine with 2 antennas for 2 rooms, usually you'll need to step this up. And this also is because you're probably covering a very large space. And so what you see here is in the very top is antenna combining units. So it's the opposite of the distribution units. We're actually taking antennas from, in this example, 4 zones or 4 rooms. We're combining those so that we have 1A and 1B that then feeds into our antenna distribution box. And then you'll notice that that box, which is a different model than what we showed before, accommodates up to 5 direct outputs. So again, this now gives us 20 channels of wireless that it's flexible across 4 different zones, 4 different rooms based on the layout. So again, there are ways to do a lot of combining and distribution to where you're not having to purchase 12 channels for this room, 12 channels for this room, when you're only going to use 4 sometimes, but then hey, maybe we do want we want 18 channels for one event that happens 3 times a year. So a lot of flexibility, really important. And again, we've got tons of information on our website if you want to dig a little bit deeper into that. Now, moving on from the really fun stuff of distribution, we're just going to look at some scan data so that you have a visual. RF is obviously something that you can't see or taste or smell or touch. So just want to walk through some things just to give you visuals of environments. And with that, I'm going to kick this over to Vanessa, since I've done enough talking for a minute here.
Mm-hmm. Thanks for that great overview, Michael. That was great. It wasn't too it wasn't too much in detail either. So I think we're good. So let's break it up a little bit and let's jump into a poll question. So we're going to switch gears here. So if you would, please take a look at the scans on the right-hand side of the screen here. And we're going to flash a poll in just a minute here. But we want you to tell us what you think the difference is between these two scans. So again, two scans up and bottom there. You can see, maybe take a look at it, think what possibly could be the difference between these two scan data plots. And we're going to open up that poll question right now. So please vote away.
Okay, poll is launched. So everybody get your answers in. All right, it looks like at 65%, we've got pretty much everybody that's going to chime in. So I'm going to close the poll here and I'm going to show you the results. All right, it looks like most people think that it was that the antenna gain changed, and then it's kind of almost a tie between the other three options. So let me close this poll, hide the results, get back to the presentation here. So I'll kick it back to you two to give the answer.
All right. So the answer is, now day and night, there is possibility that that can potentially cause an increase or decrease of RF signal. But what you are actually seeing here is the difference of the antennas, what you see in the bottom picture, kind of there by that lift, that is inside of the building. And then in the top picture, you'll see there top left, the two same omnidirectional antennas. Those are outside the building on a little platform. This is 33 stories up in a major metropolitan area. So this is actually positive because what you see in the bottom picture there, which is inside, you can actually see how much of the glass in the building structure is actually reflecting and attenuating outside RF. And so this is important of why scan data is very crucial when doing final coordination or any type of RF spectrum planning, because this gives you the visual of what is actually going on within the environment. So this is a way to help judge. If you remember back to that chart where you saw some G band listed or H band listed, this will help you decide, can I get away with the G band in this, or because of the amount of spectrum, do I actually need to move to a different series of product that gives me a more flexible tuning range for me to cover a little bit more of the spectrum to get all of my channels in. So it's simple things like this. This scan, literally each scan took about 90 seconds to complete. So these are things, again, that are quick and simple to do to really get a grasp on what your environment is doing. And then I think we kind of just covered that. I kind of talked through this slide. But the key takeaways, again, you saw all of that RF. What you didn't see in that picture was a football stadium that literally was like a block away that you almost looked down into. So again, you think about firing that up on a Sunday or a Monday night game day, and you're going to get a lot of other broadcast and other interruptions as well. So those are the some of the things just to be aware of that are in your environment that Vanessa kind of mentioned earlier as well. Now, continuing to move on, Vanessa's got some really cool information on a DECT project overview, and we're going to see a different part of the spectrum and just kind of show you what that looks like. So kick it back to you, Vanessa.
Thanks, Michael. So we're going to jump right into my tale from the field, if you will. And as you'll see on the next slide, we're going to talk through a project that I encountered. And in this particular case, I was actually called in. This was a bustling metropolis, if you will. It was a downtown urban environment, and there were multiple DECT systems on a floor. So, more than one system operating in the space. And we were called in to help troubleshoot an issue in which the system just in one particular space was not particularly reliable. It would work sometimes, and then other times it would not. Now, what's interesting here is that the system had been installed about 4 years prior. Of course, we had this thing called the pandemic in the middle, which the system had little to no use. So we were trying to determine what could have changed in that particular time frame. You know, why would the system work perfectly fine for a couple years, and then now we're just getting some issues? So what we did was utilize the built-in scanner on the MXW APT to help pinpoint the issue. And if you go to the next slide, Cheryl, please, you'll take a quick look at a few examples in terms of what we saw with that built-in scanner. So at the very top is the maybe not so good view, right? So in this example, we had little to no channels available for our system to operate. This was the problematic space where, you know, the microphones would work, and then unfortunately there would be some interference which would overcome the system. As we kind of walked down the hall, things started to open up. Things looked a little bit better. So we had moderate to good availability in that better example. And in that best case example, we had quite a bit more of availability. You'll see that green color, you know, green is good, yellow is caution, and then red is certainly not good, as you see above. So what we did was, you know, of course it seemed to be located to that room. It seemed to be that the interference was coming from that particular room. So we took a look around. We asked if there was any call centers or office headsets that maybe had gone in. And unfortunately, there were not. So still, we're utilizing that scanner, trying to see where potentially that interference could be. We're using our eagle eyes to look around the room, and we discovered that there was some sort of an antenna, which we couldn't quite determine what it was. Turned out to actually be a cell repeater. Now, this cell repeater itself was operating in the 2.4 gigahertz range. When we looked into the settings of that particular device, it was set to its highest setting, and it was operating on a whole plethora of channels. So there was some bleed over into the 1.9 gigahertz. We finally convinced them to try to turn that off just to see what would happen. And boom, the access point went green. So we were able to operate those channels when that unit was off. But of course, that's not a scenario that would work. So we did work with them to adjust the power setting and the operation channels on that cell repeater. And we were able to get both systems to work reliably together. So scanning can be super important. Being aware of other DECT devices in situations can also be super important as well. And with that, I'm going to kick it back to Michael Moore to talk through an example of the 2.4 and 5 gigahertz range. Michael?
Awesome. Thank you, Vanessa. Great images. So last piece here of parts of spectrum to show you 2.4, 5 gig. Again, large metropolitan area. And what was kind of unique about this is that the MXCW product, while we were there, we were actually doing scans like you just saw from MXW because they were going to leverage some of that product. They were going to leverage UHF band as well with other product. And so, you know, kind of while you're there, you might as well just scan all parts of the environment because there was other future use for specific to MXC for them in this part of the spectrum. So again, just trying to take snapshots of every part of the spectrum that we can do while we're on site so that you really get that full picture. So again, what you'll see on the next slide is going to be the actual output. So similar to, you know, to the MXW access point, the MXCW gives you this look into the environment. Now, again, what you'll see here that the access point icon is actually on a DFS channel. So we talked about those earlier. So it lives on these open channels. And if you look across that image, you'll see all of the green channels, which just simply means those are backup channels that this access point can jump to if it does find any interference on the existing channel. But you also see some other channels too that have some orange on it as well. It's not that you cannot operate on these channels. It just simply means that there is an increase in the noise floor. And with anything RF like that, an increase in your noise floor when you're operating within that part of the spectrum usually just means that you've got a limited distance that you can go. So you can still use some of those channels, but really based on what we saw throughout the building scans, if they needed to deploy this product, there wouldn't be an issue getting this device up on the air. So again, it is seamless switching. So one of the benefits when you look at devices like this, because it is a true two-way transceive between the delegate units, between the access point, that anything like this, it gives you, and because it's digital, you get great security, you get seamless switching. And so it's just, again, more spectrum, more things to look at that's quick and easy to give you a visual of what your environment is doing. Now, to kind of round this out, we talked about the quick, easy way that we just did DECT and 5 gig and 2.4 scans. But what we didn't start out with when we showed you that poll was how do we scan for UHF, which is what a lot of folks use. And I'm going to kick it back over to Vanessa to go through the importance of scan data and then how do we acquire this scan data.
Awesome. Thank you so much, Michael. That was a great example. So let's talk a little bit about UHF. As we mentioned with DECT and 2.4 gigahertz, we have the access points for the MXW, the MXCW that we can use to access that scan data. That's super important. With UHF, we have things like receivers or transmitters. Now, each of those devices, whether it's a Shure device or something else, is going to have something like a group or channel that is going to be coordinated to work together. So you can actually scan those devices and find that best available group and channel for your area at a given time. Additionally, there are things like spectrum managers, which are going to be that AD600 or AXT600 that you see there, which are going to give you a big overview of the spectrum that you have in that particular area. So you can utilize spectrum managers. You can also utilize receivers to access that particular scan data in your area. There are, of course, third-party devices that are available as well, which sometimes have a screen on them, like you'll see with the AD600, that gives you that snapshot of that spectrum. And they may have software available as well. But these hardware tools will pair beautifully with the software solutions on the next slide. So with the scan data that's coming out of our receivers, coming out of our spectrum managers, we're able to utilize a software tool, Wireless Workbench, for example, or others that are third-party software, which is available. And this will give you the availability to actually see those TV channels. You'll see what other operators might be in your area so that you can properly coordinate all of the wireless systems in your facility or in your particular location. So it's a really, really helpful tool to make certain that you're operating on the best free and clear channel in your room. Now, as we move on, there are other tools which are available in your wireless toolbox. So of course, Wireless Workbench, we have things like Shure's Audio Institute. We have tons of educational information if you're interested in learning more about this topic and more. We also have things like frequently asked questions on the website where you can actually type in a topic or type in a question, and you'll very likely find the answer there, or you'll find some guidance in terms of where to go with that particular topic. So really great tools available to you as well. In addition to that, we have some online tools. Now, Michael had done a wonderful job walking through some of these tools, some of the math behind this, but we do have a wireless accessory wizard, which is going to help you get a list of recommended accessories and connection diagrams based on your wireless system. You can also use the remote antenna calculator for the recommended antenna configuration. It'll step through some of that math for you. And we also have a wireless frequency finder that is really a database that's searchable by your address and zip code. So a number of really, really great tools available to you as well. In terms of just bringing it on home, wrapping it all up for you here, it's really important to, again, make certain that you're conducting that needs assessment, that you're understanding the project requirements. Michael talked about this earlier, but things like channel count, usage, transmitter type, and application are going to be things that you're going to want to keep in mind. You're going to want to narrow down which system is going to work best for you. So you're going to estimate that usage. Do I need a few channels? Do I need a lot? What is my application? That's going to be super helpful in terms of narrowing down which RF system will work best for your application. We definitely want to scan. We want to scan during the design phase. It may sound a little bit early, but it's important to get that information as early as possible so that we know that we're utilizing or planning for the proper system in that location. We're going to want to choose the proper frequencies for your environment. Again, you can do that if you're using a UHF system with the group and channel scans. You can also use things like spectrum managers to help you do that. And it's also important to scan again during that commission phase to make certain that those frequencies that you thought would work are definitely going to work. And remember to always think about frequency scanning if you encounter an issue which may be related to that frequency that you're operating in or that spectrum that you have chosen. And again, we've got lots of reps, we've got tools, we've got Sure support, we've got frequently asked questions, which are available to you as well. So with that, I think we're going to open it up for any questions, unless Michael has 2 cents that he'd like to add. 2 cents, 5 cents?
5 cents, just a dime. Great job wrapping it up, Vanessa.
Are there any questions, I wonder?
Yes, we do have a couple of questions. All right, so let's dive in. Great presentation, lots of great information, and I think we have some good questions here. First question is about DECT. Is the latency in DECT a concern for sound reinforcement applications?
So, I mean, I could jump in here. I think it could be, depending on sort of the room size, and maybe if you're utilizing the standard density mode or the higher density mode. We didn't really talk about that too much, but if you're looking to accommodate more channels in either because of your channel count or because it's a tight RF environment, it's possible that that increased latency with that higher density mode could be problematic. But in some cases, if it's just a light voice lift and depends on other components in that chain, it may be okay. So it is sort of, it depends, I think. It's always the answer, right?
Of course, definitely. All right, next question. DFS is operating in 5.1, 5.2, and 5.4 gigahertz, correct? This is a radar frequency as well, just to confirm.
Yes, and one thing that is, again, we didn't bring it up, not to make it a product presentation, but one of the ways that, and we're not the first ones, to be honest. It's not like we just discovered this part of the spectrum and hey, we're going to use this. It's actually been used by other manufacturers before, but there's not been what makes our product different and keeps it very robust and reliable is that because this is used by DoD and FAA for high-res Doppler radar, so you'll see a lot of this around potential military installations as well as airports. We actually have 2 transceivers built into that access point. So one is scanning, looking for any of those other signatures that we are required by FCC to remove ourselves from that channel and quarantine it, and then rescan it until it's a clean channel, and then we can consider going back to it if we need to. So it is utilized in those situations, and by FCC rules, this allows us with the 2 transceivers to work very efficiently and consistently in that environment.
All right. Next question is about antenna cables, I believe. Can you point us to a good chart that shows the loss per foot on various cable types along with loss per connector?
Yes. So in that FAQ that Vanessa mentioned, I believe there is a chart that will show you the difference in, for example, RG58 versus RG8 versus RG8X versus RG213. There is a chart in there, and a part of SAI as well. There is also courses on antenna distribution that will help basically tell you which one. And in fact, on those tools, online tools, I think it's the Accessory Wizard.
Yep.
It will actually tell you what we would recommend as a cable length. So there's a lot of tools and resources out there where you don't have to necessarily memorize it.
Awesome. All right, next question. You have to consider RSL based on microphone transmitter too, correct? And do all Shure mics have the same transmit power to consider for design?
Based on the difference in part of the spectrum, they transmit at different power settings. So what you'll find in milliwatt output and UHF versus MXW DECT versus 2.4 or 5 gig, they do have differing transmission power output, which is also one of the reasons why you're allowed to stack certain things a little bit tighter in those spaces by manipulating your output power.
Okay. Next question. My understanding is that the FCC does not allow our secondary transmitters to operate on UHF DTV bands where licensed stations are present. So even if I can't see RF signal inside the building, can I still use that DTV channel?
There are a few technicalities that allow you to operate on what would be a DTV station, and I believe it's based off distances. I don't want to quote anything specific here, but there are ways, even if Wireless Workbench shows you that within that scan data, you saw some exclusion zones that were set up because based on what your zip code is, you can actually go in and it'll automatically tell you what DTV stations are there. But I believe there is some distance parameters set up to where you can legally operate on some of those channels.
Okay. Next question. Regarding scanners, can you make any recommendations for third-party spectrum scanners?
I don't know that I know of any. I've heard of like RF Explorer. I think that's the main one that I hear about a lot. I don't know if you've heard of any others, Michael.
I've not, and I just lost the name of the file. It's specific to the file type that Wireless Workbench accepts. And I don't know why I just blanked on that file type, but it's a scan file that as long as it creates and saves that in that file type, you're allowed to upload that into Wireless Workbench to coordinate.
Okay. Can you share the scanning setups that were used in the field examples for DECT and UHF?
Yeah, I was going to say I'll cover the UHF because I did those. That was a multi-story building that had wireless from, I believe it was like the 12th floor to the 33rd floor. And so we literally just got a hand cart and took a AXT 600, our Spectrum Manager, put a laptop on that. And then you'll notice those pictures were a set of our 860, which is a wideband omnidirectional antenna. And the reason why in that scenario we used omnidirectional, one, the building wasn't built out yet, which you saw. So what you're really scanning for is anything environmental. And so you wanted to use the omnidirectional antenna to look 360 degrees. Now, I will say that had that building already been installed with directional antennas and we were doing a renovation or we were doing a wireless system add to it, you would typically scan through the existing installed antennas so that you can see what the receivers are seeing based on that. You can take an omnidirectional in and do a general scan, and then you can save that data and then also scan from the existing installed antennas. And then that gives you kind of an A/B comparison of what is 360 degrees in the environment and then what your antennas are actually receiving, which also actually helps you kind of troubleshoot the system to make sure that you're seeing consistent RF into the scanner from both sets of antennas, which also goes into the whole antenna cable loss, antenna gain scenario. Sometimes just by having a freestanding set of antennas will help with doing some of those A/B scans.
Thanks. And on the DECT side, I guess I would say that we did also utilize the MXW APTs that were installed in the facility. So again, it was a city environment. I think we were on floor 8. They had a couple different floors, but this just happened to be their conferencing floor, if you will. So we went in and took a look at what we were seeing with the existing antennas in their locations to try to get an idea of where that interference might be coming from. We swapped antennas in the problematic space. We did put additional access points in there to see if was it an access point issue, which would be extremely rare, and it was not. So we were able to, again, determine that interference just kind of by looking around and looking for other decked sources of interference, that interference was that repeater that was in use in that particular facility.
Great. All right. Next question. Is intermodulation distortion more common in one area of the frequency spectrum than another?
Who wants it?
I can't answer it, so it's on you two.
So intermod, because of digital transmission systems, is significantly reduced a lot of that. What we used to experience, it was a much greater effect in analog world because of the analog transmission itself versus digital transmission and the way that it transmits, because it is a different modulation scheme when you go to digital. And one of the benefits of that is that you reduce the amount of intermods that you have, but you still do need to pay attention, especially when you get into utilizing any wireless device at a higher or max power. That's, you know, one of the things when you go to a higher density mode in some of our UHF's product, it actually reduces the output of the transmission power in order to accommodate and reduce the intermod effect.
Okay. All right. Next question. Can you go over the modification needed to the UA211 when using multiple antennas?
Oh man, sounds like somebody got burned on this before. So yes, the 221, there is a component level inside of that device because it can be used as a combine or it can be used as a split. Now, the thing to remember that if you're splitting an antenna across two receivers, bias that gives power to an active antenna for the amplifier built into it does not like to see bias voltage from another receiver. And so that's the reason why that little diode is installed in the device itself. And so you simply pop the cap off of it, remove that, and then now you can utilize it to feed bias in both directions. But there is a reason why that is set up like that.
All right, great. And I think that just about wraps up our questions for today. So if you do have a question that we somehow missed or that pops into your head afterwards, you can go to shure.com/contact and fill out a form there to get in touch with our applications engineering support team. We have a great team of guys and gals that can answer so many questions across audio, RF, all of the above. So go to shure.com/contact for any questions you have that you can't find in the FAQ or in the tools on our website. We want to thank you so much for joining us. I hope you learned a little something. I know I certainly did. And we hope to see you on the next one. Have a great day, everybody.